In this lab, we're going to be examining a compound that you make with infrared spectroscopy and using the information from the infrared spectroscopy to identify the compound. The way that we can identify a compound is through its functional group. The different functional groups have specific vibrations, and these specific vibrations allow us to say, oh, we see this bond vibration in this wavelength, and so that wavelength corresponds to this particular functional group. And infrared is considered the standard for identifying the functional group in a molecule. In addition to that, there's a region of the absorption spectrum that we call the fingerprint region, which is all the absorptions of all the little tiny bonds, the carbons and hydrogens and the carbon-carbons, etc., all over, and they make little tiny absorptions in a broad range, and that pattern of absorptions will exactly match to a compound. If there's a slight change in the compound structure, there's usually a huge change in the fingerprint region. And so you match peak for peak, intensity for intensity in this region. The intensity of the peaks is directly related to the magnitude of the bond dipole and the number of bonds. So you have a lot of carbon-hydrogen bonds, so the carbon-hydrogen bond peaks tend to be very big, and they have a big enough dipole that they're infrared active, is what we say, meaning they will absorb in the infrared region. A lot of carbon-carbon bonds are invisible or have tiny peaks because of the lack of polarity. But the carbon-oxygen, the carbon-nitrogen, carbon halide, oxygen-hydrogen, and the nitrogen-hydrogen bonds have a huge dipole, and so they make really large intensity absorptions for just one bond. And so those are helpful in identifying functional groups. Infrared light is shined through the sample. The sample will absorb some wavelengths and not the others, and then the detector is able to process the information and present it to you as a spectrum. The key functional groups that we are to know about, first of all, the carbon-hydrogen bonds, and there are 3 locations where you find carbon-hydrogen, one for sp3, one for sp2, and then one for sp. An oxygen-hydrogen bond in an alcohol, and it's easy to recognize because it's broad and in a particular location. Then an oxygen-hydrogen in a carboxylic acid, which is almost in the same region as the alcohol, but it spreads out much wider, and you have almost a messy spectrum because it's so broad. Then there's the carbon-oxygen double bond, aldehyde and ketones, and you also have it in acids and things like that. There's a particular range for an aldehyde and a ketone. Nitrogen-hydrogen bonds, which are very close to where the oxygen-hydrogen bond absorbs, but the appearance of the peak is much different. Then you have carbon-oxygens that are in alcohol, esters, and carboxylic acids. These tend to be in the fingerprint region and so are hard to use for identification, but you can. And carbon-carbon double bonds, which are real easy to identify that area. It can get a little confusing sometimes because they're close to the carbon-oxygen double bond, but usually it's very easy to distinguish them. You can find a table of absorptions on page 864 in your laboratory textbook. A scanning IR is an old-fashioned one, and what it does is it uses a prism to shine only one wavelength of light through the sample, and then there's a simple absorber on the other side that says either light's coming through or not and what the intensity is. And then it plots this or records it into a computer as the prism rotates and goes through all the wavelengths. There's a much more advanced type of infrared spectrometer called a Fourier Transform IR, and what it does is it shines all the wavelengths at once and then has a computer decipher the response afterwards. And so you're able to use a split beam, and the computer analyzes the absence of wavelengths from the Fourier transform wave. And with this advanced computer, the calculation can be taken back to the simple wavelengths. And this is what we are going to use. It's much faster and a much better instrument. So now you understand that an FTIR instrument shines the entire sample at once with all of the wavelengths, and then the computer is able to decipher the spectrum. When you look at the spectrum, what you will see is wave numbers. Wave numbers is 1 over the wavelength. And why? Because wavelengths tend to be very small numbers. Wave numbers are larger numbers. So it's much easier to deal with those numbers. I guess that's why they did it. It wouldn't bother me to have the tiny, tiny numbers with exponents on them, but someone must have thought that it was simpler. So you're going to see the wave number instead. The sample must be pure, so you want to purify before taking an infrared spectrometer. A mixture is very hard to interpret and it's very misleading. The sample should be anhydrous, and the reason is that salt crystals are used in the instrument, and the salt crystals will either become clouded or erode away if there's enough moisture. If there is moisture in the atmosphere or moisture in your sample. If it is a liquid, you're just going to place a drop on the sample holder. It's called an ATR that holds the sample holder, and you close the chamber and then run your IR. If you have a solid, what you have to do is use a special clamp that you place on the ATR, and you press it down so that it's in close contact with the sample holder. I will show you how to use it and observe your operation of it as you use it, because it's a very expensive machine.